All right. We are almost done with chapter 4. We should finish it today. I want to finish talking about free radical halogenation today. I'm going to move on to chapter 5, talking about alkenes. I did enable the next Learning Smart module for chapter 5, so that's available. And for right now, I kind of have it planned through next week, Wednesday. We'll see how we go in the chapter. It may be extended from there. So if we don't finish the chapter by then, it'll be extended longer. I have it on good authority from ITS that they are working on getting the Chem plugin installed on the cluster computers. Some have been implemented in IAC already, I think, in some of the clusters there. And they tell me by Friday it should be campus-wide on the campus computers. So that means we'll be able to use the Chem on the campus computers, which means I'll be doing some more problems. So look for that. I'll probably enable it later this week, one of the chapter 5 problems, and we'll give that a try again. So any questions on that? All right. Another thing I wanted to mention, there's going to be 2 days this semester that I'm actually going to be out of town. One of those is next Friday, the March 2nd, and Monday, March 26th. And so what I plan to do, we won't have class on those days, but I will be posting a lecture video. So you'll be responsible for watching the video and getting the information there for those 2 classes that I'm doing. Okay? Easy enough? Okay. All right, well, let's continue talking about free radical halogenation. So remember, on Friday, I know that was a long time ago, so let me refresh your memory. On Friday, we talked about this process of making alkyl halides by a reaction mechanism involving activation of something like chlorine gas, Cl2, molecular chlorine, with heat or light to break apart into free radicals, and then that is reacting with hydrogens on carbons. It's one of the few reactions that alkanes will do. And it actually forms a mixture of products. Mostly the monohalogenated product is what's formed. And we were talking a little bit about details of this mechanism. So one of the species which is generated is there are these reactive carbon radicals. Those are carbons with unpaired electrons, where electron is missing, so it doesn't have an octet. So for example, these carbon radicals have only 7 electrons around them in the valence shell. And their stability mirrors that of the stability of carbocations that we've talked about. So the more substituted the carbon, the more stable it is, the lower in energy those radicals are. And that has an impact actually on this free radical halogenation mechanism, because you have faster reactions or easier to break CH bonds to form radicals when the radical is more stable. Okay? The stability of that radical is due to the similar reasons why carbocations or empty orbitals on carbons are stable. That's because of hyperconjugation, mostly, to help satisfy that electron deficiency. So again, free radicals are deficient of 1 electron. And we looked at a little bit of information about the bond strength, or the enthalpy, the energy of various types of bonds, in particular carbon-hydrogen bonds, and we can see that the bonds become weaker as the carbon they're attached to is more substituted. So primary hydrogens, that's hydrogens on a primary carbon, have a certain bond enthalpy, the energy required to homolytically break that bond. And if you go to more and more substituted, a tertiary, let's see, here's the tertiary hydrogen, 95 kilocalories per mole. So it's a weaker bond, takes less energy to break, which means it breaks easier and is more reactive. Okay? That impacts the type of results we see when we carry out a free radical halogenation on alkanes, which have different types of hydrogens. In this case, of the reaction of butane, and we do the chlorination reaction, we see 2 products formed because there are only 2 different positions on butane. One being the chlorine attached to the primary carbon, and one being the chlorine attached to the secondary carbon. Okay? And if you just count statistically the number of hydrogens that could have been possible to replace, you would predict that that ratio would be 3 to 2 or 6 to 4. But in fact, it's the other way around. And that is reflecting the difference in the reaction rate of the different kinds of hydrogens. So in this molecule, we have a CH3 here and a CH3 here. There are six primary hydrogens, right? But they're harder to break. They're harder to come off than these hydrogens which are on a secondary carbon. These are the 4 possible hydrogens which would lead to the second product there if you replaced any one of those with a chlorine. They're easy to break, so they react faster, and so you end up getting the mixture is not a statistical mixture, but based also on factoring in the reactivity. And so we see that just based on what we would expect and what we actually get, we can predict that secondary hydrogens are 3.5 times more reactive for this free radical halogenation reaction than the hydrogens that are on the methyl groups, the primary hydrogens. And likewise, in the bottom example, we talked about this one also. There are 2 different positions on this isomer of butane, 2-methylpropane. One of them is a tertiary hydrogen, so there's 1 tertiary and 9 equivalent primary hydrogens. And we don't get a ratio of 9 to 1, it's less than that, which means the tertiary hydrogens must be more reactive. It's coming off at a greater rate than what statistical numbers would suggest would be the case if it were equal reactivity. Okay? That is reflecting the nature of the radical intermediate. Because the tertiary radical that would be generated initially along the reaction mechanism path for this tertiary carbon is lower energy, and it's faster to make that radical than it is to generate the primary radical because of its higher energy or lower stability. Let's see. There we go. So if we take a careful look at the mechanism, for most reactions in this class, we talk a lot about reactions forming and breaking bonds involving 2 electrons. But in this case, we're talking about forming and breaking bonds where we're talking about 1 electron moving or 1 electron breaking. So in this case, the reaction is started by activation or cleaving a chlorine-chlorine covalent bond. So this is done under the action of energy either produced by absorption of a photon of light or by a significant amount of heat. Okay. Either one, if you've given enough energy, will break this covalent bond, giving 1 electron each to each of the chlorines. So we break it again homolytically. And then we have generated reactive free radicals. These are reactive species because, again, they are deficient of electrons. Chlorine now in its valence shell only has 7 electrons and it wants 8. Right? So this process of starting from a stable molecule and homolytically cleaving a bond to generate 2 or more radical species, this is what we refer to as an initiation step. And what we see in this process for free radical halogenation is that the reaction is a chain reaction. Theoretically, if you only added 1 photon of light and broke 1 chlorine molecule, the reaction then to do chlorination of an alkane would occur over and over and over again forever until the reagents were used up. Theoretically. In practice, we see that the reaction doesn't keep proceeding on its own completely. And I'll explain why in a second. So that's the initiation step. First, you have to form these chlorine reactive species. Okay. Now, to actually start making bonds to chlorine to the carbon, we first have to break a bond because in this case methane is completely saturated. There's no place for the chlorine radical to add to. So we have to first pull off a hydrogen radical. And that's done by a radical species. And that is the free radical of chlorine that we've generated in that first initiation step. So what happens now, chlorine wants to satisfy its octet. It has the ability then to pull off a hydrogen atom with its one electron and form a covalent bond. And that then sends one electron to the carbon. So what we have happen in a step which we refer to as a chain propagation step, we start with a reactive free radical, and then we react that with a stable molecule. And we've generated now a new stable molecule by breaking and forming bonds, and a new free radical. Okay. Now we have this methane radical as our reactive species. Okay. So this is step 2, part of the chain propagation portion of this mechanism. Hydrogen atom is reaction by the chlorine radical. Okay. Now, once we've generated a reactive carbon, then that carbon can react with another molecule of chlorine in a propagation step. So trying to maintain this chain reaction, we need a free radical species reacting with a stable molecule to form a new stable molecule and a free radical which will continue the chain. So again, a highlight or a hallmark of chain propagation step is we have a radical in the left side of the equation, and we've generated a radical that appears in the product side of the equation. Okay, and it's just the same way. This is the reactive radical. Carbon wants its octet, and so it will take a chlorine from that Cl2 with one electron. The other electron goes to the other chlorine, so that bond is broken. This new carbon-chlorine bond is formed, and we have generate a free radical. This can now continue the chain reaction, and if it encounters another molecule of methane, okay, what's going to happen? Well, it's going to pull off a hydrogen and form HCl again and a methyl radical, right? That methyl radical then can react with another molecule of Cl2 and so on and so on. This is the chain reaction process which could take place. Okay? So why doesn't it go on forever? Why do we have to keep irradiating our reaction vessel with light or keep heating it to keep the reaction going forward? Because there are other possibilities. What happens if instead of a radical and a neutral molecule coming together to generate a new radical, we just bring two radicals together? In that case, we don't generate a product which can continue a chain reaction as a reactive species. And this is what we refer to as a step, as a termination step. Okay, a termination step. One example, which would actually give the product for our chlorination reaction, if the methyl radical which is generated encounters a chlorine radical, they can just combine those electrons to form a new covalent bond. Okay? A free radical species plus a free radical species forms a stable molecule and nothing else to continue the chain. So that would be a dead-end path, right? Still give the product, but another molecule couldn't be activated. And so that would terminate the process. And so if that happens, in order to continue our reaction going with more of the molecules, we would have to add more light or heat. And that's why we can't do this just forever with one photon. Are there other chain termination processes you can think of? What are all the species we have present, all the radical species we have present in this reaction? Well, we have methyl radicals and we have chlorine radicals. They could combine to form a carbon-chlorine bond, as I've shown here. So what happens if two chlorine radicals come together? That could happen, right? Chlorine radical plus chlorine radical. What would that form? Cl2. Right. That's the opposite of the initial reaction we talked about, initiation or breaking apart Cl2. That would certainly stop the not forming another reactive species to continue a chain. That's happening also. Okay? What's another chain termination reaction you could think of involving these species? Methyl radical plus chlorine radical can form chloromethane. Chlorine radical plus chlorine radical can form chlorine molecule. Yes, methyl radical plus methyl radical, right? If we react this with another methyl radical, now I didn't put that as a product before, but if we combine those two together, what are we going to form? Ethane, right. We'll join them together with a covalent bond. By the way, higher alkanes could be a possibility in this, although they're trace amounts. If you look carefully, you might see that they are formed in this process. Okay? So, this free radical halogenation reaction practically isn't that good in most cases. As a matter of fact, on that first, let's see, do I have this on the next slide? I think I might have added this slide here for you. Yes, so this is the overall reaction I showed you before. Look what else is present, okay? I didn't add ethane, but ethane could be produced. But look what else besides the product, of the major products, HCl and chloromethane, you can form dichloromethane or trichloromethane or tetrachloromethane, okay? Because once you start producing CH3Cl, what could happen with that? Well, we have reactive chlorine radicals present. If we react it with CH, instead of methane, it encounters a CH3Cl, what would happen? Chlorine pulls off a hydrogen to generate now a chlorine-containing carbon radical. And then if this encounters Cl2, you're going to put a second chlorine on. And then that product, this product, could react with another chlorine radical to pull off a hydrogen and so on. And so you have these as trace byproducts as well. It could all happen. The amount of them really depends on how much is there at any given time, the various concentrations of these things. So as a reaction proceeds, you have lots of molecules around. As the reaction proceeds, your mixture of molecules in your reaction vessel and the ratio of them are going to change. So bottom line is, for simple alkanes, for small alkanes, free radical halogenation is a useful process for generating, oh, I didn't have it here. Sorry, it's a useful process for generating chloroalkane. Methane, there's only one kind of hydrogen. Something like, let's see, it works okay with something like, I don't know, cyclopentane. It's got 5 hydrogens in it, I'm sorry, 10 hydrogens in it. If you replaced any one of them, you'd all get the same product because it's symmetric, right? Doesn't matter which hydrogen you replace with chlorine. The product you get, the major product, it doesn't matter where you put the chlorine on there, it's all going to be the same product. It's when you have branched alkanes where the positions aren't all equal. Butane is an example, you get a mixture of products. It's not that practical for a synthetic procedure because it's not very selective. When there's no other possibility, of only possibility of one product, it's not that bad. The type of halogen actually makes a difference for that. I'm not going to go into details, I'm not going to worry too much about bromination, but when I talked about those differences between 2-methylpropane and getting a tertiary chlorine or a primary chlorine, when you do bromination, it's a little more selective than chlorine, and that has to do with the ease of breaking bromine bond as well, because both partners are involved. So it could be a little more selective with bromine and perhaps iodine, but I'm not going to worry too much about that. What I want you to have as a take-home message for this is that the radical chain process that occurs, you need to know you don't have anything happen until you can initiate radicals to begin with. And then once you do that, there's a process of 2 steps of the chain propagation that continues that over and over again. And then there are pathways which can terminate those kinds of reactions. Okay? So that's how halogenation using these free radical methods works. We will learn that there are other ways to make alkyl halides that are better. We talked about a few of them here, right? Replacement of OH for a halogen, using SOCl2 or PBr3 with alcohols. Those are better, more selective ways because we know where the alcohol is, and that's where the chlorine or bromine ends up. Okay, your book doesn't go into a lot of details about the radical stability, but I just want to mention something about radicals and carbocations. We talked about the fact that this on the left is our molecular orbital picture of the carbocation showing the sharing of electron density by the adjacent CH bonds, the hyperconjugation, or the free radical sharing adjacent electron density by hyperconjugation. That's one way, the substitution to stabilize radicals and carbocations. We talked a lot before talking about lone pairs and negative charges that those charges are stabilized by delocalizing through resonance, right? The same is true for both radicals and carbocations. So if you take a look at these 2 examples, if we have a carbocation adjacent to a double bond, okay, the charge of that empty orbital, that electron deficiency is actually spread out, and we can draw 2 resonance forms. So if this plus charge is an empty orbital, and there are 2 electrons in the double bond adjacent to it, you could move those 2 electrons over to form a new double bond and then leave the other end of the carbon deficient. And that gives the plus charge over on this side, and then those 2 electrons are here. Okay, and back. So you can draw resonance forms for carbocations, which are adjacent to pi bonds. And just like we were talking about lone pairs or negative charges, if you think about those 3 carbons in a row, okay, the carbocation is an empty p orbital. I'll put a plus charge there, empty p orbital. And next to it is a double bond, which has a pi bond with electrons. So it really is not existing one side or the other. Resonance is something in between. And so the 2 electrons in this pi bond just are spread out across all 3 adjacent carbons. Or further, if you have more double bonds. Benzene rings. Things adjacent to a benzene ring. And the exact same situation is true if you have a free radical. A free radical next to a double bond is also that electron deficiency, or the missing 1 electron is spread out at the 2 ends. So if you imagine, again, 2 electrons in that pi bond here, 1 going over here to form a new pi bond, and this one going on that carbon, you could draw or imagine the electrons moving in such a way to form the other resonance form. Okay. The principle's the same. It's 3 p orbitals in a row. This one, double bond having 2 electrons in it, and then a p orbital with just 1 electron in it. And so that electron, it's just all spread out. That's what resonance really means. So when we think about these free radical halogenation, I just want to mention this for your information. The book doesn't talk about this at this point, but if you have something like this, and you have methylbenzene, or what we call toluene, free radical halogenation occurs quite readily and very specifically at this carbon next to the ring. So if you react this, for example, with bromine and heat, I'm running out of room here, you get a very selective reaction putting the bromine on that, where that CH3 was. You replace one of those hydrogens on CH3. It's not atypical, just a primary hydrogen. Because along the way, the intermediate, you form bromine radical, and then you pull off a hydrogen, and then you form a radical on that carbon. Well, that radical is greatly stabilized because you can delocalize it into the ring. You can draw resonance forms, spreading it all the way around through that ring. That's much more stable than just a tertiary radical because of the delocalization. And that's something that will come up later as we go into further chapters. I mention it here because we're talking about carbocation and radical stability. It will be important later as well.
So
yes?
The free electron is going to delocalize to the adjacent pi bonds.
Just like the double bond, so if I just draw one resonance form, sorry, this is a little small, can you see that? You can draw it there. Then you could move it down here and then shift one electron up here. So then the radical could end up there and then up there. Just like we moved a negative charge around when we talk about resonance, we can do the same for free radicals or carbocations. Okay? That's the connection I want you to make because the concept is really the same. Delocalizing charge or free radicals. Okay? Any other questions on free radical halogenation and stabilities of radicals and carbocations? Okay, I'd like to talk more details about alkenes and how we make alkenes and their properties and how the formation of alkenes by elimination reactions has some similarities and connections to the reaction mechanisms we've talked about for substitution, SN1 and SN2. It's kind of like the opposite of SN1 and SN2, actually. So we'll talk a little bit about that. So let's talk about alkenes. Okay? Structurally, we know that something like ethene, 2 carbons, has sp2 hybridization, and that pi bond, or the double bond, is made up of 1 sigma orbital overlap in the middle. So there's a sigma bond, and then we have a pi bond, which is 2 p orbitals overlapping side to side. Okay, so I want you to think about that in terms of its 3-dimensional structure. The hydrogens, all of the atoms, our nuclei, are arranged in a plane. Okay, the carbons and 2 hydrogens are all in one plane. The electron density that's in that second bond between them and the pi bond is above and below that plane. Okay, and in order to bond, it has to be fixed in a certain orientation. And that's important also. One of the things that we use to describe alkenes is their general formula. The general formula for an alkene is CnH2n. Where have you seen that before? CnH2n is a general formula for a cycloalkane. Just like the cycloalkane, if you have a ring, you have to remove 2 hydrogens to connect the 2 carbon ends. The same thing is true for an alkene. In order to form the second bond, you have to lose 2 hydrogens. So the general formula for an alkane is CnH2n plus 2. For an alkene with 1 double bond, 1 pi bond, is CnH2n. But we know that molecules aren't just that simple. We have molecules which have more than 1 double bond. We have molecules which have combinations of double bonds and rings, right? Doing both, each time you form another pi bond or another ring, you have to lose 2 hydrogens. So this general formula, as we talk about, really is only true for a molecule with 1 ring or 1 double bond. And we refer to molecules according to their degree of unsaturation. Unsaturation, well, saturated molecules are what we refer to for alkanes. They have as much hydrogen as possible to have all single bonds. Okay, those are saturated molecules. Unsaturated molecules are ones that have double bonds or rings. right? You hear about monounsaturated oils or polyunsaturated oils and fats. Those are fats which have carbon chains that have double bonds in them. So it's easy. One of the things, though, if you have more than one, we want to know what the degree is, how many pi bonds or rings we have, and it's a pretty easy formula to think about that. So here you can see we define degrees of unsaturation as a simple formula. So the molecule, we take the number of hydrogens if the molecule were completely saturated, subtract the number of hydrogens that are actually present, and adjust that for other atoms, and divide by 2, because each time we form a pi bond or a ring, you have to take 2 hydrogens away. So that's the generality of the formula. Here is more specific. So 2n plus 2, n is the number of carbons. That's the formula for a saturated alkane, right? So that would be the blue part of that equation. Minus the number of hydrogens that are actually present in your molecule. Okay. But we have to adjust some things. So if you have a halogen, chlorine, bromine, iodine, fluorine, how many bonds does a halogen make? 1, right? So if you have one of those in your molecule, it has taken the place of 1 hydrogen. Okay? But not by forming a pi bond or a ring. It's just if you have a fluorine bonded, that's in place of a hydrogen. So you need to consider that like it was a hydrogen. So minus the number of hydrogens, minus the number of halogens. And then because nitrogen has an odd valency and would add 1, you need to add the number of nitrogens. And overall, this should tell you how many pi bonds and rings you have. And it's a useful way to think about looking at molecules, or if you have a molecular formula, you can easily determine if you might have this many double bonds or rings present. Let's say you have an unknown molecule, but you know the molecular formula. This is a good clue as to whether there are double bonds or not in your molecule. So let's just take an example. Let's take a molecule. Let's see. Something like this. Okay. What's the molecular formula? C5H1234 NCl. Okay. You should easily be able to, if you didn't know the structure and you just had the molecular formula, you should be able to figure out the degrees of unsaturation. How many pi bonds or rings or combinations of those there might be. So the formula is quite easy. Carbon number is 5. So 2n plus 2, if you put 5 in for n, that's 12, right? 2 times 5 is 10 plus 2 is 12. Minus 4 hydrogens, minus 1 chlorine, plus 1 nitrogen. So what does that equal? Was it 8, 7, 8? No, that's not right. Yeah, that's right. Everything divided by 2, that's 8 divided by 2. That's 4 units of unsaturation. So this molecule happens to have 3 pi bonds and 1 ring. That's 4 units of unsaturation. 4 times we'd have to take 2 hydrogens out to make that structure. So this formula actually works every time if you need to figure out or get some clue as to the number of pi bonds and rings. Okay, make sense? This is something also your book doesn't introduce, but you'll use a lot later when you talk about spectroscopy as clues to figure out structures. So it's useful to know. So degrees of unsaturation. Let's talk a little bit about naming. There's some additional things you need to know for the naming rules for alkenes. And a lot of it is similar to the IUPAC rules we've already talked about. So you need to find the longest chain in your molecule, which contains the double bonds, or a triple bond, or whatever. Those pi bonds, the double bonds, they get preference over a chain. So if you have a longer chain which doesn't have the double bond in it, it doesn't matter. The chain has to include the double bond. Then you number the chain nearest the end of the double bond. Okay? Even if you have halogens, halides, or alkyl substituents, so if you have methyl groups or chlorines, fluorines, something like that, closer to one end, you still need to give the double bond the preference. So you number on the end closest to the double bond first. And that's where this priority of the alkene is important. That being said, it's a little confusing because once we have an OH group or an alcohol, it's the alcohol which gets priority over a double bond. So alcohols somehow rise above the double bond. Alkyls and halides, less priority than the double bond. And then when you name it, what we do to indicate that it's an alkene is to replace the ane ending with ene to indicate the double bond. Okay? And we have to give the number of the position of the double bond. So some examples are shown here. You can see several examples of alkenes. So in this case, we have a 6-carbon chain. The double bond happens to be between carbon 1 and carbon 2. So we always give it a number referring to the first carbon the double bond starts at. So even though it spans carbon 1 and 2, we refer to this as 1-hexene for that molecule. As opposed to 2-hexene, 2-hexene would look like that. The double bond starts on carbon 2 and goes to carbon 3. Okay. Sometimes you see that number for the alkene put within the parent name itself as opposed to being out front. That's perfectly acceptable as well. So you might see this called hex 1-ene or hex 2-ene for this other example I just drew. So that number, if the number is out in front, it's referring to the alkene, or it's put right before that substituent. Sometimes names get very complicated that it's a little more clear if you put it here. Especially if you have more than one kind of pi bond system in your molecule. If you have alkenes and alkynes and things like that, you want the number associated with it. So you might see that as well. Okay. The second example, the longest chain containing the alkene is a 4-carbon chain. We can number it in this direction, which is what the correct name is, 2-methyl, 2-butene. Notice if I were to number it from the other direction, the double bond would still start at 2. Okay? So either way you number it, the alkene is on the 2-carbon. So that really isn't the distinction between numbering it from one side or the other. If it's the same numbering from both sides, then you go to the alkyl substituent. In this case, the methyl group is closer to the left side. So we give that the number 2. Okay, make sense? Not that hard. Here's a ring here on the bottom right, a cyclohexene. There's 6 carbons. The double bond gets preference over chlorine substituents. And so you have to number the ring starting the number 1 carbon from one of the ends of the double bond. So if you number starting from here, the double bond gets preference, you would have to number the carbon 2 here, carbon 3 here, carbon 4 here, carbon 5, and 6. Okay? That would give the alkene starting at 1, and since it's a ring, that has to be the 1 position, so it's not even listed in this name. But the chlorine would be in the 5 position, numbering it that way. We can get a lower number if we start numbering 1 here and number the other way around the ring. It's still 1 cyclohexene, but then the chlorine is now on a lower number. Okay, so be a little careful with rings. You got to start from one end of the double bond is 1, and then 2, the other end of the double bond. And the direction you do that matters for other substituents. Okay, and if there are more than 1 double bond, we use the prefix for that that indicates the number, so it's a diene if you have 2 double bonds. If your molecule has 3 double bonds, it's a triene, tetraene, pentaene, etc. And so we have to give numbers for both. In this case, to get the lowest number, the alkene numbering would be the same from either direction, but the lowest number for the other substituent then would be this. So the number here refers to the starting position of each double bond. Since there are two double bonds, there are two numbers. So 1,5-hexadiene is the parent, with a methyl group on the number 3 carbon. Okay? So again, the alkenes get preference for finding your longest chain and for initial numbering. If it's the same either way, then you go to the substituents of alkyls and chlorines for the lowest number. But not until all alkenes have the lowest number first. If you have an alcohol group, the alcohol outranks that. So even though the double bond is within the chain of the carbon, an OH group outranks it, so we have to start numbering 1 here. So this is so how would you name this molecule then? Longest chain is 7, so what would you call it? Heptene. Oh, that's right. And this is a little complicated because we have two functional groups which both add to the end of the name. And so if you just put the numbers in front, 1, 5, it makes no sense, right? So you could do that. There are a couple of ways you can do this. Since the alkene is at 5 and the alcohol is at 1, you could say, let's see, you could say 1 hept 5 ene all. That's a little confusing. You could say 5 hept ene. Actually, there's no e there. 1 all. You could actually put that number with the all. Or probably the clearest way to do something as complicated as this, I would probably say hept 5 ene 1 all. So I think that e's not there. I have to double check that. You might get confused with that. So that's actually the most clear way to do it. Put the numbers within the name to show the ene and the all, and then it's the least confusing way. To make sure the right number is with the right, and I forgot something else here, something should go in front. 6-methyl. Okay, so that would be prefixing that. Okay? Questions on naming? There are some common names which refer to molecules which have unsaturation of the alkene type, which you will see, especially when they're referred to as substituents on groups. So here are some examples. If you have a double bond, which is attached, that 2-carbon group attached by a single bond to a larger molecule, this is what we refer to as a vinyl group. That's a word you've heard, right? Vinyl? Well, maybe not. You probably don't have records anymore, right? Has anyone ever seen a record made out of vinyl? What is vinyl?
Plastic.
It's a plastic made from vinyl chloride. PVC, polyvinyl chloride. Well, that's PVC. There are other kinds of vinyls. It's a polymer made from molecules like this. So you can see where that name comes from. This is a substituent as a vinyl group, and so if we use a common naming and you call this a chloride, it's a vinyl group on a chloride, so it's a vinyl chloride. If we talk about a molecule and we want to describe the hydrogens which are attached to a double bond, these are sometimes referred to as vinylic hydrogens. Okay? Like a hydrogen attached to a tertiary carbon is a tertiary hydrogen. This is a hydrogen attached to a sp2 alkene carbon. It's a vinylic hydrogen. Okay? I might refer to it that way. If there's another carbon group in between, so this is completely a 3-carbon group where you have a double bond, CH2, CH, and then a sp3 carbon attached to something. This is what we call an allyl group. And you might see that referred to allyl alcohol, for example. Again, alcohol is being the parent. This 3-carbon group is referred to as an allyl group. And we often refer to hydrogens adjacent, on the carbon adjacent to a double bond. They're on an sp3 carbon. They're adjacent to a double bond. We often refer to those as allylic hydrogens. Okay? Allylic hydrogens, if you have a free radical bromination reaction, they come off quite easily because you form a radical next to a double bond. That's what I was just talking about before. So it's important when we talk about some of these more reactive things. A 3-carbon group, there's another common name. A 3-carbon group that's attached not on the sp3 hybridized carbon, but on the middle sp2 hybridized carbon. If it's attached there, we call it an isoprenyl group. Isoprenyl bromide, for example, here. That's not used quite as commonly, although you might see that. That's what that means. And then this is a hard one because if you want to talk about something like a double bond not within the ring, but going off of a ring, like this case, we refer to this as a methylene group, a CH2 group. This word methylene has a couple of meanings, one of them being a CH2 group on the end of a double bond attached to something else as a substituent. Sometimes it's referred to as just a CH2 in the middle of a carbon chain. That has a slightly different meaning. But in the context of alkenes, it's usually something at the end of an alkene bond. So you may see that as well. I don't need you to necessarily be able to tell me this back and remember that completely, but if I refer to them that way, and particularly when I talk about allylic hydrogens or vinylic hydrogens and things like that, you should know what I'm talking about, and that's important. Okay, one other aspect of the double bond structure, remember it's sp2 hybridized, and we have a pi bond, which is a bond which is a side-to-side overlap of p orbitals, both above and below the plane of the atoms that are in there. You'll notice the bond angle is about 120 degrees. We've talked about all the sp2 structure before. The bond length is shorter than a single bond carbon-carbon bond length. That pi bond tends to pull it a little closer together. The electron density of a double bond actually is in that pi system above and below the plane of that nucleus. And reactivity occurs there. We'll talk a lot about reactions of double bonds later. One of the consequences of a double bond is that it's a stronger bond, because if you were to think about the bond dissociation energy, to break both of the bonds, to break 2 bonds would require more energy than to break 1 bond, right? So if you look at a carbon-carbon single bond, the energy required to break that apart into 2 carbon radicals, that is about 375 kilojoules per mole for the single bond. That's the sigma bond between the 2 carbons. To break a double bond into breaking both bonds homolytically to form those very, very reactive species, that requires 730 kilojoules per mole. So based on that, can you tell me which is stronger, a sigma bond or a pi bond? A pi bond is weaker than a sigma bond because you notice if you just take the single bond, which has a dissociative energy of 375, and double that, what's double 375? 750 kilojoules per mole? Right, so both bonds should, if you just doubled it, if the pi bond was as strong, the energy to break a double bond would be 750 kilojoules per mole. It's only 730 kilojoules per mole. So 375 of that is for the single bond between it. That means the pi bond is a little weaker. Okay? That's important to recognize because when we do chemistry with alkenes, we're doing reactions to break the pi bond. And if you remember from the beginning of the class when I talked about sigma bonds and pi bonds, the sigma orientation of an end-to-end is a better, stronger overlap than a side-to-side overlap. And that's reflected here in the bond dissociation energy. Okay, I'm going to stop there today and we'll talk more about double bond structure and how it impacts isomers for double bonds on Friday.